Hello, my name is Henk Nijland. I'm an application engineer at TerHoek HenkNijland. In this presentation, I would like to tell you more about precision electrochemical machining, or PECM. TerHoek is your partner for precision problems like high tolerance, low surface roughness, etc. We use a variety of techniques to produce high accuracy parts. This presentation will zoom in on the PECM technology. Precision electrochemical machining makes contactless high-accuracy machining of metals possible and is commonly used to produce complex, difficult-to-machine parts, mostly in large series. When compared to other techniques, PECM has certain advantages like no contamination and high service quality. PECM is a clean process. This table is from a test case. As you can see in the highlighted sections, no additional elements were found on the surface. There is one remark. It is possible that electrolyte residue will leave some deposits on the surface. Those can be removed by cleaning. A cleaning step may be required. Like stated before, it is possible to produce parts with high surface quality, depending on the electrode roughness, the current density, and the material. Higher current density equals higher surface quality. In PECM, all edges are rounded. This is a normal result of PECM and ECM. At TerHoek, we use the PEM 800 machines from PEMTech. The machine consists of the PEM mechanic in the middle, which is the actual machine, the PEM Aqua on the left, which is the electrolyte processing plant, the PEM control and PEM power on the right, which contains the generators. The machine can deliver up to 9,600 amperes. At this moment, we have 3 of these machines. This is a schematic representation of a PECM machine. On top, we see the oscillator suspended in leaf springs inside the Z-axis. The cathode or tool is mounted on the oscillator by a 0-point clamping system. In the same way, the anode or workpiece is mounted on a table. Electrolyte flows in the working gap between anode and cathode. The process can be explained in 3 steps. In step 1, the machining gap is opened. Fresh electrolyte flows into the gap. In step 2, the machining gap is closed. A current pulse is triggered and the material is dissolved. In step 3, the machining gap is opened. The dissolved material is flushed out of the gap by the electrolyte. In this video, you can see the electrode moving up and down. Just before the lowest point, a current pulse is triggered, shown by the red line. Dissolvement takes place when the current pulse is active. When the electrode moves up, dissolved material and heat are flushed out. In the meanwhile, the Z-axis moves toward the workpiece at a preset speed. In PECM, there are 3 possible operation strategies to remove material. The front forming operation is the most accurate approach. It has mu range, accuracy, and high surface quality. The front cap is usually between 10 and 30 microns. When machining into the surface, there's also a side cap operation. The side cap operation is less accurate and has lower surface quality due to the lower current density. Circumferential or so-called side cap operations are used to make splines, sprockets, leaf springs, etc. Mostly, this operation is performed in existing holes or gaps. The accuracy is lower compared to front-forming operations. In polishing or so-called ECM operations, the main goal is to improve surface quality, but we can also use it as a material removal strategy. The electrode is set in a position and pulsating power is applied. In side cap polishing operations, the oscillator is switched off. In front polishing operations, the oscillator can be used to improve flushing. At TerHoek, all PECM tooling is designed and manufactured in-house. using all machining techniques that are available to reach the precision needed for high-end PECM tooling. Often, tools evolve from a simple testing tool to a single-piece tool and then to a large series production tool, as shown in these examples. Electrode shapes are important. When a straight, non-coated electrode is used, the sides will be at an angle. The process will continue to erode the sides as the electrode advances into the material. The gap will get bigger and the current density lower. An undercut electrode will reduce this effect. When the sides need to be straight, the electrode will need to be coated and mostly also undercut. Making undercut or coated electrodes is more complicated and will increase tooling costs. Finding a suitable coating in combination with the correct application method for the electrode model can be challenging. Electrolyte flow rate and pressure are important parameters in PECM. The electrolyte flow conducts electricity and transports heat and sludge. Both have a direct influence on the service quality and the generation of flushing lines. The flow in the working gap changes constantly due to oscillation. Especially in cross-flow applications, the flow changes drastically as displayed by the schematic. In T0, there is a laminar flow in the working gap. In T1, the electrode moves down and disperses the electrolyte outward. The incoming flow is slowed down. In T2, the electrolyte is near the lowest point and the dispersion is at a maximum. Almost no new electrolyte enters the working gap. In T3, the upward movement of the electrode causes a vacuum, and the electrolyte enters the working gap from both sides. In T4, we are back to the starting point. Flow chambers are used to ensure optimal electrolyte flow between the cathode and the anode, and to pressurize the electrolyte in the working gap. Pressurization helps to control the size of the gas bubbles in the electrolyte. Gas bubbles can be seen as potential insulators. Pressurizing helps to reduce or even eliminate the bubbles. It also helps to control the flow rate at a higher pressure. If the flow rate and the flow speed are too high, the surface may contain flow lines due to erosion. If the flow rate is too low, the electrolyte will be saturated, resulting in a non-optimal process at the runout area. This is another example of in-house produced tooling for front cap operation. The tool is shown upside down. In this case, the flow is directed by the rubber flaps mounted behind the electrodes. This design allows us to ensure electrolyte flow when machining difficult shapes. This is a view from the other side where the electrolyte exits the tool. At this angle, you have a good view of the electrodes. So, a short recap. With PECM, we have no heat-induced zone, no micro cracks, no stress, no contamination, high service quality, low tool wear, and high reproducibility. Because PECM is not widely known, most parts are designed for known production techniques. PECM allows you more freedom in design. PECM has numerous advantages. Most of them I have tried to explain in this presentation. However, there are also some disadvantages, like longer engineering and prototyping phase. But high producibility and multi-processing tools lower the product price, making PECM a reliable and cost-efficient production method. With this overview, I will end this presentation. I hope my story has given you more insight in PECM. If you have any questions, please don't hesitate to contact me.